with that sort of introduction, I think kind of our first order of business here is to look at the fuel cell. We've said we want these inlet and outlet temperatures. How do we go about figuring out what the airflow has to be? So let's start with the fuel cell. And let's further start with a control volume. So if I'm going to use red here, here's our fuel cell where we've specified the inlet and outlet temperatures. I call this control volume number 1. That's the control volume that I want to consider with an open system balance. And if I just write out an energy balance, assuming we're operating at steady state, we want to keep everything constant with time, then our control volume would look like this. We have 0 equaling the sum of all the incoming streams of molar flow rates n dot I HI minus the outgoing streams plus heat and work. And I think I was arguing earlier, we don't have any heat because there's no way to get heat out of a stack directly. We can remove materials, but that's already contained in our outlet flows. The other thing, we have electrical work, which is leaving. And the way we've defined electrical work is positive outward. So I'm just going to subtract from this WE dot. So one of the first things we have to do is, what is the electrical work? That's the part we've already been talking about. We know that's our 20 kilowatts. And so if I kind of relate that to our fuel flows, electrical work, this is NF times V of the cell times the fuel utilization times N dot H2 in stream 1. So stream 1, actually, yeah. So the hydrogen comes in stream 1. It just gets heated. So that's the same flow rate in stream 3. And that's what goes into the fuel cell. So N dot H2 in stream 1, we're using up 80% of that as it goes through our fuel cell. That's the incoming hydrogen. And so we can rearrange this, and it's going to say that N dot H2 in our incoming stream has to equal the electrical work divided by 2F times V cell times fuel utilization. So as we vary V cell up and down, we vary in terms of the utilization up and down. The amount of hydrogen we need to produce that 20 kilowatts goes up and down. So N dot H2 in stream 1, we can work through. This is 20,000 joules per second to 96,485 coulombs per mole. We've got 0.7 volts, which is a joule per coulomb. And we're at 80% utilization. Coulombs cancel, joules cancel. 0.185 moles per second. So that's the hydrogen that's flowing in. That's constrained already by mass balance. Okay, so the rest we have to work out by material balance and or energy balance. And the way I'm going to suggest doing this is using a enthalpy table. What I want to do today is go through in some detail an Excel spreadsheet that I set up to do this, to try to keep everything fairly straight and make use of the automated calculation tools in Excel to allow us to quickly go through and calculate enthalpies at various temperatures, some of which might be things that we're solving for. First of all, I wanted to draw a flow sheet. I flow sheeted it last week, but this is a little bit more detail. The other thing I've done here is I've tried to be a little bit more explicit about the heat exchangers. Normally, You can't really have three streams going through a heat exchanger, preheating of fuel and air. So I've split the function of that one heat exchanger that I was talking about into two. One of them heats the hydrogen, the other one is heating up the air. So what we're doing is we're taking the exhaust out of the fuel cell. The exhaust from the cathode is stream 6. The exhaust from the anode is stream 7. And those are going into the afterburner or tail burner, as it's sometimes described. We basically burn up all the remaining hydrogen because oxygen is in excess for reasons I talked about last time. The combined exhaust, which is now going to contain combustion water, unused oxygen, and all the nitrogen that came in with the air. That's in stream 8. So I split that into two streams, 9 and 10. Stream 9 goes to the first heat exchanger that's preheating the air. The other part of that goes to a smaller heat exchanger, HX2, which is preheating the hydrogen. So hydrogen comes in this case, at 25C. Air is coming in at 25C. We're preheating those up to the temperature we want in streams 2 and 5, and then those are going into the fuel cell. And then as a last step, I'm taking the exhaust from the two heat exchangers, and so we're recombining them into stream 15 to send out as exhaust. The way usually I set these things up is I try to identify in the problem that I'm working on what variables are going to be inputs. These are things that are not things you're solving for. They are quantities that constitute the major, control knobs that you have over your process. And we've talked about some of that, but one of them is the cell voltage. We can pick what cell voltage we're operating at. I'm also going to specify the fuel utilization on the stack. So how much of the fuel comes in is actually going to be consumed electrochemically. I have to pick a basis as well. And in this case, I've decided to use a fuel basis, not a power basis. For a given amount of fuel, how much are all the other flow rates going to be and how much electrical power will we get out? You could also flip this around and specify electrical power and then solve for the number of moles that you would have to flow through. Either way works perfectly fine, but you do somewhere have to pick a macroscopic or an extensive basis. One of the variables I didn't talk about last time, I've got this exhaust, I've got to split it in two to send it to these two different heat exchangers. And the way I have this set up right now, I'm specifying what percentage of the exhaust goes to the hydrogen preheater versus the air preheater. I'll come back to why I've set it at the particular value I have, but it's adjustable. One other last detail, usually the hydrogen is pre-humidified. We don't have purely dry hydrogen. So I'm assuming it's a fairly simple operation here. We're just taking hydrogen. You might be bubbling it through water and humidifying it. So I'm assuming 1% moisture, and that's adjustable. You can change that. And then finally, the stack temperature. What's the stack temperature? And this is going to be a constraint that is going to affect the enthalpies of all the gases coming out of the fuel cell. And then down here, I have variables that I am solving for. And I haven't quite finished this yet, but I have the air flow rates. This is one of the things we're solving for. How much air do we need to go through the stack to keep it at steady state? How much electrical work are we going to get out of the stack when we're all done? And then other things like the higher heating value efficiency or the reversible efficiency. And we'll come back to calculating that. One of the things we've kind of gone through is it doesn't matter how many cells are in there. We know the cell voltage and we know the fuel utilization. Through Faraday's law, we can figure out exactly what the electrical work would have to be. And it should be, let's see, 2, because we've got 2 electrons per hydrogen molecule, 2F times B5, which is the utilization. And we're also multiplying by the cell voltage. And I think we're getting that in kilowatts. So yeah, 108 kilowatts is the power that we're producing. We can calculate that right away without doing any energy balances because we already know the cell voltage and utilization. So just color coding, blue I'm using for knob turning kind of quantities, things that I'm setting as a requirement or a constraint. Red are things that I'm iteratively solving for using some type of indirect solver like GoalSeek or Solver. Green are post-processing quantities, things that I'm calculating from the input variables. So our first one here is electrical work. which we can just straight calculate from cell voltage and utilization. And then down here, I have another table. This is a table of temperatures. So I'm specifying all of the streams. I'm giving them a temperature. Some of them I'm specifying, other ones I'm solving for. And other ones are going to be just slaves to the funds that we're defining. So for example, stream 1 and stream 3, which are the input of the air and the fuel, I'm just going to define those to be 25 degrees. So those are the input gases. The other thing I'm constraining here is streams 2 and 5. And by that I mean we're going to specify the input temperature of the gases going into the fuel cell. So I set the stack temperature at 700 in this example. I'm setting the input gas temperatures at 500 as the value that we want to maintain for the input temperature. With those constraints, we can do an energy balance on the fuel cell. The last thing I need here is a table which has all the thermo data summarized. I've got basically 4 species in this problem: the nitrogen and oxygen that are coming from the air, and we have hydrogen, and we have water. All of them have enthalpy for a formation of 0. So because they're elements, except for water, which has a negative enthalpy of formation. And you'll notice it's minus 241. So what I'm talking about specifically here is H2O gas. These columns I'm not really using. This is delta G of formation, delta S of formation. This is important if we're going to be calculating equilibria, which we're not in this problem. So the only columns that we care about here, remaining columns that we care about, are from the heat capacity correlation. So I've gone back to the back of Koretsky, and I've looked up terms A, B, C, and D for the heat capacity correlations for these 4 molecules, so that we can integrate, integral CPdT to calculate enthalpy changes from 25C up to whatever temperature we're operating this material, whatever the stream temperature is. With all that, we should be able to calculate, if I know the temperature, basically, I should be able to calculate the enthalpy of any of these species. So with all that, I think we're in a position now to set up the enthalpy table. And I think you guys have done this certainly by hand in the past. And if not, you've seen this done in Excel too. But basically what we're doing is we're imagining a control volume around this fuel cell. We've got streams 2 and 5 coming in, and we have streams 6 and 7 coming out. And so what I'm going to do is I'm going to list all of the incoming species, and I'm also going to list all of the outgoing species, and then calculate their enthalpies. So that's what this is. The way I do the material balance is I just do it right here on the spreadsheet using cell formulas. So for example, if we look at the nitrogen, I've set over here, I've set up a cell which contains the airflow. I'm later going to adjust it, but if I specify it right now, I can take that airflow and then calculate all the other stuff. So nitrogen, for example, is 79%. So I've typed in equals 0.79 times this cell. So whatever this airflow is doing, I'm adjusting, I'm calculating the nitrogen that's contained in the input. And then oxygen, same thing, 21% of that airflow is going to be oxygen. The hydrogen is just the basis, so I picked that as 1 mole per second. So I'm just copying my basis over. And then the water, that's 1% of humidity. So the hydrogen is our basis, and I'm specifying how much additional water that we're sticking in stream 3. Whatever water content is in stream 3 will also be in stream 5. So this is the list of mole flows for all of the species. And then over here, this is the outflows that are coming out in streams 6 and 7. Nitrogen doesn't react, so it's just going to come out. I'm just typing it in as, equaling the input value. The oxygen will be consumed depending on how much we're reacting. That depends on our utilization. So we know that whatever that oxygen is, I'm going to take that amount. So K27, that's the cell containing the input oxygen. And I'm going to subtract from that any oxygen that reacts away. I know what the input flow rate is of the hydrogen. multiply that by the utilization. That tells me how much hydrogen we're consuming. And then I'm multiplying that by 0.5 to indicate how much oxygen we would similarly be consuming in that electrochemical reaction. So based on the utilization and the fuel flow, we can calculate how much oxygen we're going to use up. So that's what that is. And then the same thing for the hydrogen. Hydrogen 1 mole goes in, and we calculate that minus the utilization times the fuel flow. And so it's 80% utilization. We should be left with 0.2 moles. So when 1 goes in, we're using up 80% of it. So 0.2 moles remain in stream 7. And then water, we go in with 0.01 moles. We come out with 0.81 moles because we're taking H2 to H2O, and we've got the 0.01 that we fed in originally. So a total of 0.81 coming out. So that's the mass balance, right? That we've done our mass balance. All the species in, all the species out, and then the enthalpies. And in this case, we're not solving for the temperature. We've actually specified the temperature. So we're saying we want the outlet temperature to be 700 degrees. We want the input temperature to be 500 degrees. So we know the enthalpies already from that. So this is the whole formula typed in. Basically, I've taken the heat capacity correlation A plus BT plus C T squared plus D over T squared or whatever, all those terms, and integrated. So integral of C P dt, you integrate all those terms analytically, and you're going to get 4 different terms. So it's looking at enthalpy of formation. It's adding to it R times the integral of all these terms. And so there's the A term. It's going to have the difference in temperature between the stream temperature minus 298, which is the reference temperature. The next term is going to have the temperature squared minus 298 squared. Third term, cubic term in it. And then the last term is reciprocal temperature minus the reciprocal temperature of the reference state. So you notice the enthalpy of formation of N2 and O2 and H2, they're all 0. The reason I'm including it in the formula is I want to be able to copy and paste the formula without worrying about which species is what we're talking about. We're just moving up and down which row we're describing. So if we look quickly over here on the left, Excel highlights which cell are being used in the calculation. So once I've debugged this formula and made sure it's working, then I just copy and paste it to every single cell in the whole thing. So you can see which temperature it's referencing, stream 2. So if we think about which species we're talking about, it's the air. So stream 1 is turning to stream 2. Stream 2 contains nitrogen and oxygen. So I want the input temperature of stream 2. And that's what we see. So you can move this up and down. You can grab this cell and move it. Oops. You know, if you want to change the temperature, which stream you're talking about, you could just move the reference up and down. There's 4 references because there's 4 terms, so I got to move them all at the same time. But that's one convenient way to change which stream and which species you're talking about just by moving these cells up and down. Okay, so it's referencing temperature stream 2, and this is nitrogen. And so if I want to switch to a different compound, again, I can just adjust these up and down. Move it to oxygen or whatever you want to do. So this is just sort of a convenient thing to do with Excel. And then the oxygen, similar thing. I've just moved down a row from nitrogen to oxygen, and that gives us the oxygen. And then the H2, I just moved down another row, and I've switched temperature to stream 5. The temperature of stream 5 and 2 are the same, but I like to keep it straight. In principle, I could set a different temperature for this for stream 5. And then finally the water, that's also in stream 5. And so I'm making a column of N dot, I'm making a column of H. This is in moles per second, and here's joules per mole. And then I'm multiplying together. So this is N dot H for each species, which is just a multiple of N dot times H. And then I just copy that down, and then this is the sum. So this is the sum of N dot H for all the input substances. And then on the output, I do exactly the same thing. So again, same formula. I've just adjusted which row it's addressing and which temperature it's addressing. In this case, stream 6 is the nitrogen and oxygen, and stream 7 is the hydrogen and water. And then I'm taking that nitrogen, excuse me, N dot times H, multiplying together and adding those up. And so if we think about our energy balance, we've got sum of N dot H in is right here. And then this is the sum of N dot H out minus the electrical work. So the electrical work should be the same one we calculated over here, 108 kilowatts, and it looks like it is. So then over here is the difference. So this is electrical work out plus N dot H out minus N dot H in, and that should be 0. And it is 0. And why is it 0? Because I already solved for it. So let me just show how to do that though. Let's say I guessed wrong what the airflow is. Let's say I guessed it should be 20 moles per second. What you see, if I go back over to here, is the energy balance is no longer obeyed. We are in deficit by 41,000 joules per second. And that's because the airflow is too big. We are cooling too much. If I lower the airflow rate to like 10 moles per second, then the energy balance is in excess. We have too much thermal energy and we're producing too much and we are not cooling enough. So that's where the adjustment comes in. We want to adjust this airflow rate up and down until finally this energy balance is obeyed. I guess you could do that manually, or you could use a tool. For a simple one cell adjusting for one cell objective function, this is basically our objective function. We want to drive it to 0. We can use goal seek. So if I go to tools, goal seek, it's going to bring up a window. And I want to take this cell and I want it to adjust to 0 by changing my source cell. And that's what I'm going to do. I'm going to specify the n.air as the adjustable parameter. And then you say go and boop. Okay, and so it has adjusted, automatically adjusted using a least squares algorithm. It has adjusted this flow rate, airflow rate, until it has met the specified target.